Good evening, everyone. Today, I'd like to continue to talk about Zksync. Now we are going to talk about a system contract, which is on L2. The word system might sound a little bit scary, but actually, it's not as complicated as we think. The system contract over here, I already listed most of the system contract from first deploy all the way to here L1 messenger. In particular, L1 messenger, I put in red, yellow color. It's going to send the message and the log to the L1 blockchain over here. Okay, so this serves the contact point with L1. Today we are going to do a little bit more focus on one of the contract which we call interesting. I haven't put over here. I'm going to put it in right now. It's called MsgValue. Let me put over here. How about put over here? Okay, it's called MsgValue Simulator, and surely this contract is going to be interacting with it's going to interact with L2 base token. Okay. Because why? Because what is MsgValueSimulator for? It's actually used to handle. If you call a transaction with MsgValue, means you are going to call a function with along with some Ethereum transfer. So typically the function is going to be called payable. Then MsgValue is going to handle the transfer and then forward the call with the call data, and then without changing the caller's identity. So that's why it's called a forward. In particular, the call might be system call, might be user call. So the system call bit will also be transferred. So this privileged call can be maintained in that context. In addition, it's going to ensure a sufficient gas allocation for the ETH transfer and the downstream execution. So they are going to manage some gas aspect. This part I don't quite understand well yet, but I'm going to try my best to explain it. And then it's also going to prevent recursive or invalid calls. In particular, you don't want to have the two. You don't want to allow people to call the function in the MsgValueSimulator directly. Okay, and then finally, it's going to handle call data, transfer, and execution. So let's look at the source code. So source code over here. It's not as long as we think. So it's inheriting the system contract base, which we might or might not look at today. There's a help function called ABI primes. What is this? Basically, this is actually allow us to so-called access the register. There are 9 registers in the the virtual machine, ZK EVM machine. They have 9 registers. I don't think we have it for the regular Ethereum machine. So this get actual ABI data 0, 1, 2 allows you to get register 0, register 1, register 2. In this case, register 0 is going to contain the MsgValue. And then register 1 is going to contain the 2, in other words, the real calling. And then mask is going to contain a word which have one of the bit is called a system call. So if the bit for the system is not 0, that means we have a system call over here that we need to forward. Okay, so this is an important library for system contracts. So let's take a look at today system contract helper. This get extra ABI data. how it's done over here. So so this is get extra API data. So as you can see over here, it's going to check the index, which is the register number. And then it's going to call a static call because it's read only. So using static call is going to enforce. We're not going to change the state over here. And then in particular, they are going to use a special call address, which is called get extra API data address. This is very typical for system call in easy EVM. Okay, it's not regular EVM anymore. So the Zksync EVM actually they have a special system call which is identified by the call address. So the real calling is not necessarily this one. Just consider this is a code for routing different functionality. Okay, and in this case they use the guess field. Usually the first argument is for guess. They use it for the index of the register. So the easy EVM virtual machine is going to know that you are trying to get register instead based on the second argument. And then they will also understand that you're going to get the this register. And the rest of them is always going to be fixed. So that means you only need the first two in this particular call over here. And then it's going to return over here. All of this information is retrieved from the context. And then the MsgValueSimulator is going to use a fallback function. So it's going to take the call data, which is from the original caller over here. And then this is only system call. So I'm not sure how this fallback call is called. Who called this? My understanding right now is it's just when a user trying to call a contract with a function, and when you have an MsG value specified, the compiler is just going to compile that part of the code into one that is going to be, this becomes the callee, okay? And then all the register information is going to be prepared like this. So that's my understanding. So in other words, it's going to, the compiler is going to compile a function call to a contract into a call to this MsgValueSimulator. So that means whatever call you have is going to be in the fallback part, right? So this is why you have to use a fallback, because you have no idea what function name the user is going to use, and then the call data is going to totally have all the data that forwarded from the user. Okay, so it's almost like the compiler is going to change the line of the code to a different call, something like that. Okay, so over here it's doing some gas management. First of all, it's going to check how much gas is left. Then this gas must be greater than this, because that means if it's not greater than if it's not greater than this, then the user gas becomes 0. Otherwise, we are going to take out this. So this is almost deduct overhead, I would say, using I mean, probably this is the overhead using MsgValueSimulator. And then we already talked about this. You retrieve the first 3 register here. And then this is a prevent recursive call. You don't want to a user call this MsgValueSimulator directory. That would be pretty bad, because if you do this, then it's going to be when you forward over here we are doing mimic call, it's going to call the 2, then you're going to call it yourself. So it's going to be a recursive call. We don't get into that situation. So we have to make sure the 2 is not this address. And then the value, if not equal to 0, then I'm going to do the transfer to transfer the token, that in this case Ethereum from the user. So this is the user is the caller, the original caller. Okay, and then to the value. So this function is using another system contract called real base token system contract, which is focused on managing the base token. We will talk a little bit today, but we are going to have a separate presentation for that. Okay, so let's just look at this transfer over here. So this transfer is going to be from to amount. So that this is authorized. This is a permissioned call. So only these 3 system contract can call this, and right now we are the first one. Okay, and the other 2 which can call this is bootloader formal address, which is the bootloader, and deploy system contract. And in particular, the second one is needed because when we deploy a contract, we can also transfer some Ethereum as well during construction. That's why. Okay, later on we're going to look at this and see how this is done. Okay, so basically here you manage the balance. This is more like a regular ERC20 token, but this is used for Ethereum balance instead. So just keep that in mind. Okay, then once we are done, if it's not successful, we're going to reverse. So we are not going to proceed if the Ethereum transfer is even not successful. If it's successful, then we are going to add some gas over here to ensure the continuous succession. So on one hand, before we do the transfer, we are doing some minus, but after the transfer, we are doing some plus over here. So that's interesting phenomena. It's like you have to pay the cost regardless if the transfer is successful or not. But if not, then we have to pay the additional penalty. Otherwise, after we pass this, they will give you it's like I feel it's like rebate, give you some return so you can continue with the execution. And then the next one is going to set a value for next 5 call. So what is this doing? This one is going to change the value from 250 bits to 128 bits. That's the maximum Ethereum you can send over. So it's going to set a value for next 5 call. Essentially is set this value. This is a context. MsgValue will be used. Okay, so it's a set a value for next 5 call. Let's look at it. How this is done. Set a value for next 5 call. Set a value for next 5 call over here. So it's also a system. It's also a system call. First of all, you have to whenever the input argument is not a word, and we use assembly, then we have to clean it up because Solidity is not going to do it. So we have to do n over here to make sure we only have 128 bits. The rest of them is going to be 0. And then we simply say set a context value call address. This is a fixed. The only thing interesting over here is these 2, which is the call address has to be this code, encode this function, and then this value. So that means the next. So this is going to change the context in the EVM, Zk EVM virtual machine, so that the msg.value is going to be equal to value in the next call. Okay, in the next call over here. So that's one. So in other words, this is like make sure the MsgValue is in the right value. The next one is going to call efficient call.minimal call. So we are going to pass the gas over here, the level gas with a little bit of reward over here. And then the tool is the original tool, and data is the call data we forwarded. And then this is an interesting field we need to look at. It's called who to mimic. Okay, who to mimic means who is the real caller is going to be considered in this mimic call. So this mimic call is a very special call. We are going to look at that. And then a system call is a Boolean that we forward over here. And then similarly is constructor is false because we are not constructing a new contract. This is only used when you deploy a contract. Okay, so let's look at the efficient call. This is another important library for system call. So there are many of these kind of things. So let's look at the mimic call and see how this is done. Mimic call. Okay, it's right over here. Okay. Mimic call is actually conducted by the raw mimic call. Okay, so let's consider what's the difference between mimic call and raw mimic call over here. We pass the gas, we pass the address, we pass the data. We also pass the who to mimic. We also pass a constructor. We also pass a system. So looks like the mimic call is simply a wrapper of mimic call, and then you simply verify the call result. Okay, and the call result is going to be, and then you interpret the return data over here. Okay, so let's look at verify result. The verify result is going to check if the success is success or fail. If it's a success, then we have the return data size, and then we're going to copy the return data to the memory over here with these sites. Okay. Of course, you have to copy from this address because the first word is the length of the return data, which already is assigned here. So the first word is assigned aside, and then so the verified call result basically is if it's successful, we are going to copy the return data to the memory. Otherwise, we're going to propagate revert, which is, let's see what we're going to do, which is, of course, we have error, so it's the same. Let me see. Oh, okay, so it's very much. Okay, otherwise it's simply going to copy the return data also to 0, but I don't understand why it's not return data plus 20 over here. So why this is not added? In other words, so where the return data size is going to be stored. So that's something I don't quite understand, but it's okay. So probably the revert is going to show. I think I do understand. So basically, this is just a string start with 0, and already the second argument already give the size. So we don't need to store the size anymore. It's already returned in the revert statement. Okay, so we didn't use the first word to store the length of the error message. So that's how they deal with the error message as well as the correct return result. Okay, so that's how the mimic call it works. Let's look at how the raw mimic. Okay. The mimic call, let's look at raw mimic call and how that's done. So raw mimic call is going to conduct a load file call ABI into active PTR. This sounds a little bit complicated in the beginning, but actually it's not. I will show you why it's not, because basically they are going to prepare a so-called active PTR, okay, which is a context. So what is active PTR? Let's look at the system contract load active PTR over here. Okay, system contract helper. System contract load over here. So so basically this is going to be a system call. The only thing interesting is this one. So this static call is going to return the success result on the stack, and we don't need that on the stack, so we simply pop it so that we can keep the stack clean. So in this way, we prepare our active PDR, virtual active PDR in the context. And then so this is basically the initialization, if you like. And then after we done that, the active PDR, then we are going to change the active PDR little by little. The first one is we will specify where the data offset is. So we are going to say data offset, which is in the call data, because this data is call data. So this means in the call data, what is the offset of this part? Okay, because in the call data you might have different argument too. And then we are going to using system contract help again and add into active. So let's look at this and see how that is done as well. Okay, so it's going to be another call address, and then because we use assembly and this input is 32 bytes, so we have to clean up to make sure it's only 32 bytes. And then in the same way, we use a static call over here. So this is going to add the PDI into active. It's going to add the offset of the data into the active PDR. So consider active PDR is execution context over here. All right. So the next thing is shrink to. What is the shrink to over here? Shrink to is so this is the whole MsgData length, and then this is the data length, and this is the data offset. So we're going to shrink this to this because we don't need to have all the MSG data to call over. Okay, so this is the efficiency, basically. Okay, the efficiency simply means let's consider this for a while. So let me see. Let me see the length minus the data length minus the data offset. So why don't we give a number? Let's say the MSG data length is 100, and then data length is 20, and then the offset is 30. So it's going to be 100 minus 50 is going to be 50. So why it's going to? So what does it mean by 50? It means let me see. So this start from 30, and then the length is 20. Length is it says 20. So I guess this is probably the this is probably the location of the end of the data, the offset. Okay, the original offset is data offset, but we need to add the data length, data.length over here. Okay, so okay, let me see. So this look at this. So this is actually the data offset. This is actually the data end, right? Data offset plus data length is the data end. So so the MsG data length minus the data end anyway, I think it's going to be the end of the location of the data. Let me just consider that way, and then you are able to shrink to that active because we the first one we remember the beginning, and this one we remember the end. So in this way, we actually locate the data more precisely. And then the next one is we're going to put the guess. So get a file call ABI with empty fed pointer because so now we are able to get the file call ABI using this function. Okay. Get a file OPI. So let's consider that too. And by the way, this is actually 250 bits word, and we use this function to get it, system context color. Let me see if I can find it. System context color. It's in library. System context color over here. And then I'm going to search for it. And then here's the function. So as you can see, it's just put all of this input into a word. depending on the location. So for example, the gas pass is going to be in a particular location over this. So I think the better way is just put this and show the file called API, show the whole layout. I think the ChatGPT will pretty good at doing this. Okay, let me see if I can do it pretty quickly. If not, I'm going to go over here. Show the layout of the word. Okay, so you can see. So basically, it's going to be like this. The gas use is going to be in this field, and then this is in this field. So basically, they put all these 5 arguments, the input argument, in the right bits. So that's basically what is this doing over here? Okay. All right, so that's very much the get file API is doing. Just put this into the right bits in this word, and then the final one is going to make this active PTR to be active, to be in the context, Okay. So why call file with empty fed pointer? So it's using empty fed pointer because the fed pointer is already filled up here. I think that's my understanding. Fed pointer means the pointer pointing to where the data is. So we have the beginning, we have the end. So we are very much done now where we put the active PTR. All right, so I think that's very much what we should talk about. I don't think we have anything more to say. All right, so thank you so much, and have a nice day.